step on a bathroom scale and you get a number. That number feels like the most solid fact about you, the sheer amount of stuff you are made of, pressing down on the floor. When the Higgs boson was found in 2012, the headlines called it the particle that gives everything its mass, which would make it the source of that number under your feet. But almost none of your weight comes from the Higgs. Close to 99% of the mass in your body is something else entirely, and the Higgs field never touches it. This is a story about mass, what it really is, what the Higgs actually does, and why the thing we call the answer leaves most of the question open. We will build it slowly, one plain step at a time, starting from the weight you can already feel. If you like a calm, careful look at the universe, take a moment to subscribe before we begin. So hold one simple question in mind. When you stand on that scale, where does that number really come from? You stand on the scale in the morning and the number settles. Maybe it reads 70 kilograms, maybe 90. Whatever it is, you feel it as something honest about your body, a measure of how much of you there is. That feeling is real, and it points at two different things hiding inside one word. The first thing is the pull. The earth reaches up through the floor and tugs on every part of you, and the scale measures how hard. We call that weight. Take the same body to the moon and the number drops to about a sixth, because the moon pulls more gently. You have not lost any of yourself on the trip. The stuff of you is unchanged, only the pull has weakened. The second thing is harder to feel but easy to test. Push a shopping cart and it resists you. Push a loaded cart and it resists more. That stubbornness against any change in motion is the other meaning buried in your weight. Physicists call it inertia. It does not need gravity at all. Out in deep space, far from any planet, a heavy crate would still shove back when you tried to start it moving, even though it would register nothing on a scale. So the single number under your feet is doing two jobs at once. It is telling you how strongly gravity grips you, and it is standing in for how much you resist a push. These are the two faces of mass, and for most of history no one had any reason to think they were different things, because on Earth they always travel together. Hold that word, mass, and notice how slippery it already is. We reach for it as if it were obvious, the plain amount of matter in a thing. Yet the moment we look closely, it splits. There is the mass that gravity feels, and the mass that pushes back, and behind both there is a deeper question we have not even asked yet. Where does any of it come from? That is the question this whole story will chase. When the Higgs boson was announced in 2012, the world was told that this was the particle behind mass, the thing that gives matter its heft. It is a beautiful idea, and it is partly true. But it is also one of the most misunderstood sentences in modern science, because the Higgs has almost nothing to do with the number on your scale this morning. To see why, we have to take that number apart slowly. We will follow the weight down into your body, past the muscle and bone, into the atoms, into the centres of the atoms, and finally into the particles that have no inside at all. At each step the question sharpens. At each step the easy answer falls away and a stranger one takes its place. For now, stay with the everyday picture, because it is the right place to begin. Mass feels like a quantity of stuff. The more stuff, the more it weighs, and the more it resists a push. That picture has carried people for thousands of years, and it works astonishingly well for carts and crates and bathroom scales. It is the natural starting point, the one your hands have taught you since childhood. But a good starting picture is not the same as the truth. It is a doorway. And the first thing we will do is walk up to that comfortable idea, the one that says mass is simply the amount of matter you have, and press on it until we find the crack. Because the crack is already there, waiting in the most ordinary objects around you, and once you see it, the rest of the journey opens up. Picture a kitchen scale and a bag of flour. Pour in twice as much flour and the needle climbs to twice the reading. This is the oldest and most trustworthy idea about mass, that it is simply how much material you have gathered together. Count the stuff, and you have counted the mass. It feels less like a theory than like plain common sense. The Greeks gave this idea its first sharp form. Democritus, more than 2,000 years ago, imagined that everything was built from tiny, indivisible grains he called atoms, from a word meaning uncuttable. On this view, a heavier object was just one with more grains packed inside it, or with heavier grains. Weighing something was, at heart, a way of counting its pieces. For a very long time, that was as deep as anyone needed to go. The picture grew more precise with chemistry. In the early 1800s, John Dalton weighed how elements combined and concluded that each element had its own kind of atom with its own fixed weight. Hydrogen atoms were light, oxygen atoms heavier, and you could predict how they joined by treating mass as a simple bookkeeping of parts. The whole of chemistry began to run on this idea that matter comes in countable units, each carrying a definite share of mass. For carts, flour, and chemical reactions, the picture holds beautifully. Bring two things together and their masses add. Split a thing in half, and each half weighs half. Mass behaves like a careful accountant, never gaining or losing in the totting up. Through all of ordinary life, nothing you can do in a kitchen or a workshop will break this rule. And yet there is a crack, and it sits in something as common as a magnet. Hold two magnets so their like poles face each other and push them together. You feel resistance, a springiness, as if you were compressing something. You have done work. You have added energy to that little system. Now ask the strange question. Does the pair of magnets, pressed together and straining apart, weigh more than the same two magnets sitting quietly on the table? The honest answer, which we will learn later, is yes. By a fantastically tiny amount, far too small for any kitchen scale, the squeezed magnets are heavier. Nothing has been added to them, no extra grains of matter, no new atoms. Only energy has gone in. And that energy has weight. This is the first hint that the counting picture is incomplete. If mass were only a tally of grains, then two magnets would weigh exactly what they always weigh, no matter how hard you pressed them together. The amount of stuff has not changed. But the mass has. Somewhere in that gap, between the stuff you can count and the weight you can measure, the simple story starts to come apart. The same hint appears in a wound spring, in a charged battery, in a hot cup of coffee. Each one is, by an immeasurably small margin, heavier than its cold, or unwound, or uncharged twin, purely because of the energy stored inside it. The grains have not multiplied. The energy has, and the scale, if it were sensitive enough, would notice. So the everyday idea is not wrong so much as shallow. Mass as amount of stuff is a fine first floor, and we will keep climbing back to it. But it cannot be the whole building, because energy with no stuff at all can still add weight. To understand that, we need to look harder at the two meanings we found, the pull and the resistance, and at one astonishing fact about them that puzzled physicists for centuries. They are always exactly equal, and that exact equality is the next loose thread to pull. Go back to the two faces of mass. There is the mass gravity pulls on, the one your weight depends on. And there is the mass that resists being pushed, the one a cart shows when you lean into it. Galileo, dropping things in the late 1500s, noticed something about the pulling kind that should have been impossible. Drop a heavy ball and a light ball at the same moment, and if you set aside the drag of the air, they hit the ground together. This seems wrong at first. The heavy ball is pulled harder by the Earth, so surely it should win. But here is the catch. The heavy ball, being heavier, also resists that pull harder. It has more inertia. The stronger tug and the stronger stubbornness cancel exactly, and both balls fall at the same rate. For this to happen, the two kinds of mass must match. The mass that sets how hard gravity pulls and the mass that sets how hard a thing resists moving have to be the same number for every object. Physicists call the first one gravitational mass and the second one inertial mass. There is no obvious reason they should be equal. One is about a force, the other is about resistance to any force at all. Yet in every test ever done, they come out identical. Isaac Newton took this seriously. He swung pendulums of different materials, wood and gold and glass and grain, and timed them. Because a pendulum's swing depends on the ratio of the two masses. If they ever differed, even slightly, the timing would shift between materials. It never did. Newton confirmed the match to about 1 part in 1,000 and wrote it into his work as a fact too clean to ignore. The testing did not stop. In the late 1800s, the Hungarian physicist Laundet of Ise built a delicate torsion balance, a beam hung from a fine fibre, to compare the two masses with extraordinary care. He pushed the agreement to 1 part in many millions. Later experiments, and satellites built for nothing else, have driven it further still to better than 1 part in 1,000,000,000,000. The two masses do not merely resemble each other. As far as anyone can measure, they are the very same thing. Sit with how odd that is. Nothing in Newton's own laws demanded it. In his picture, gravity is one force among many, and there is no reason the mass that feels gravity should be the identical number as the mass that resists a shove from your hand. It could have been a near match, or a loose match that drifted between materials. Instead, it is exact, everywhere, for everything. A coincidence this perfect is usually a clue. When two quantities that have no business being equal turn out to be equal to 1,000,000,000,000 decimal places, nature is telling you they are not two quantities at all. They are one thing wearing two costumes. The puzzle is not to measure them more precisely. The puzzle is to understand why they were ever counted as separate. That clue would sit unexplained for 2 centuries, a small, stubborn miracle in the foundations. It took Albert Einstein to see what it meant. He imagined a person in a sealed box, unable to tell whether they were standing on a planet or being accelerated through space, precisely because the pull and the resistance always match. From that single thought he would draw a new picture of space, time and falling. But before we follow him into gravity, we need the other half of his great insight, the one that ties mass to energy directly and finally explains why a squeezed pair of magnets weighs more. That is the equation almost everyone has heard and almost no one has been shown slowly. We turn to it next. In 1905, a young patent clerk in Bern published a short paper with a long title asking whether the inertia of a body depends on its energy content. Albert Einstein was 26, working outside the universities, and the paper was only 3 pages. Its conclusion became the most famous line in all of science. Energy and mass are the same thing, measured in different units, and the rate of exchange between them is the speed of light squared, written in symbols it is short. In plain words it says this: a given amount of mass is equivalent to a vast amount of energy, and a given amount of energy carries a small amount of mass. The bridge between them is the speed of light multiplied by itself. a huge number, about 90,000 trillion in the units of meters and seconds. Because that number is so large, a tiny scrap of mass hides an enormous store of energy, and a large pile of energy hides only a featherweight of mass. This is why the squeezed magnets weigh more. The energy you pushed into them, holding their like poles together, carries its own mass. The amount is absurdly small because you divide that energy by the giant conversion factor to get the extra weight. No scale could ever see it. But it is there, and it is real, and it is the same effect that powers the sun. In the sun's core, hydrogen nuclei fuse into helium, weigh the particles that go in, then weigh the helium that comes out, and the helium is slightly lighter. A sliver of mass has gone missing, less than 1%. That missing mass did not vanish. It left as energy, as the light and heat that crossed 93 million miles of space to warm your face. The sun is, in the plainest terms, slowly converting its own mass into sunlight. 4 million tons of it every second. The same trade runs in reverse in the world of particles. Smash two particles together hard enough and brand new particles can appear, ones that were not there before. Their mass comes from the energy of the collision. This is the daily business of a particle collider. You pour in motion, energy of speed, and out come massive particles, mass conjured from energy, exactly at the rate Einstein set. So the careful accountant from 2 chapters ago was working with the wrong ledger. Mass alone is not conserved. Energy alone is not conserved. Only the two together, counted as one quantity, stay fixed. Mass can become energy, and energy can become mass, and the books always balance once you treat them as a single currency. This changes what mass even means. It is no longer just a count of grains of matter. It is a measure of energy that is bound up and sitting still, energy locked into the very being of a thing rather than flying around as light or motion. A rock is, in a sense, a tremendously dense battery, holding energy so tightly that we perceive the holding itself as solid weight. That phrase, energy bound up and sitting still, is the one to carry forward. It is the key that will unlock the deepest part of this story. Because if mass is really bound energy, then to find where your weight comes from, you do not go looking for more and more grains of stuff. You go looking for energy, trapped and pinned in place, inside you. And the place to look is the atom. Almost all of your mass lives in a vanishingly small region at the heart of each atom, a region first found by firing particles at gold foil and watching a few of them bounce straight back. That experiment, run in a quiet Manchester laboratory, cracked the atom open and showed us where the weight is hiding. We go there next, into the nucleus. In 1909, in a laboratory in Manchester, Ernest Rutherford set 2 younger colleagues, Hans Geiger and Ernest Marsden, a tedious task. They were to fire tiny positive particles, called alpha particles, at a sheet of gold foil hammered so thin it was nearly transparent, and to watch where they went. The expectation was dull. The atom, in the picture of the day, was a soft, spread-out blob of positive charge with electrons dotted through it, like raisins in a pudding. The alpha particles should sail through almost straight, nudged only slightly. Most of them did. But a few, a tiny fraction, came back. They bounced off the foil and returned almost the way they had come. Rutherford later said it was as astonishing as firing a heavy shell at a sheet of tissue paper and having it rebound and hit you. A soft pudding could not do that. Something small and hard and heavy was sitting inside each atom, and the alpha particles that happened to strike it dead on were being hurled back. From the numbers, Rutherford worked out the size of that something. The atom is mostly empty space, and almost all its mass and all its positive charge are crammed into a central core 10,000 times smaller than the atom itself. He called it the nucleus. To picture the scale, imagine the atom blown up to the size of a great cathedral. The nucleus would be a single grain of salt at the very centre, and the electrons would be a faint haze drifting through the vast space around it. Nearly all of your weight lives in those grains of salt. The electrons, the part of the atom that does chemistry and gives matter its surface and its colour and its feel, are almost weightless by comparison. A proton in the nucleus is about 1836 times heavier than an electron. So when you step on the scale, you are very nearly weighing the nuclei of your atoms, and almost nothing else. The rest of the atom, the enormous empty space and the faint cloud of electrons, contributes hardly anything to the number. This already strains the everyday picture. You feel solid. You press your hand on a table and it stops, firm and unyielding, yet the matter in that hand and in the table is almost entirely empty. If you removed the empty space and packed all the nuclei of a human body together, the whole of you would shrink to a speck far too small to see. A speck that would still weigh exactly what you weigh now. The solidity you feel is not stuff filling space. It is the electron's refusal to overlap. A force, not a substance. So the search for your mass narrows sharply. It is not spread through your body. It is concentrated in these dense central cores, the nuclei, each one a tiny knot holding nearly all the weight of its atom. Find what the nucleus is made of and what holds it together, and you are most of the way to finding where your weight truly comes from. The nucleus, we learned, is built from protons and neutrons, packed tightly together. The proton carries positive charge, the neutron carries none, and is very slightly heavier. A hydrogen nucleus is a single proton. A carbon nucleus has 6 protons and 6 neutrons. The iron in your blood, the calcium in your bones, the oxygen you breathe. Each is just a different count of these 2 particles bound into a core. For a while it seemed the journey might end there, with protons and neutrons as the final heavy grains, the true atoms of the old dream. But they are not the end. The proton itself has an inside. And when physicists finally looked into it, with a different kind of scattering experiment at a laboratory in California, they found something that would overturn the whole idea of where mass comes from. That is where we go next. By the late 1960s, the proton was no longer thought to be a simple ball of charge, but no one knew what was inside it. To find out, physicists used the same trick Rutherford had used on the atom, only far more violently. At the Stanford Linear Accelerator Center in California, a machine 2 miles long fired electrons at protons with enormous energy, and watched how they scattered. If the proton were a smooth, soft blob, the electrons would glance off gently. Instead, just as in Manchester 60 years before, some electrons bounced back at sharp angles, as if they had struck something small and hard deep inside. The proton was not smooth, it had structure. It contained tiny, point-like objects, and the electrons were ricocheting off them one at a time. These point-like objects matched an idea that Murray Gell-Mann and, independently, George Zweig had proposed a few years earlier on paper. Gell-Mann called them quarks, a playful word he took from a line in a James Joyce novel. The theory said the proton was built from 3 quarks, and so was the neutron, in different combinations. For a while, quarks were treated as a bookkeeping trick, a neat way to organize particles, perhaps not real. The Stanford experiments showed they were real things you could hit. A proton holds 3 quarks of 2 kinds, 2 called up and 1 called down. A neutron holds the mirror set, 2 down and 1 up. The up quark carries a positive charge of 2/3, the down carries a negative third. Add them in the proton and you get 1 full positive charge. Add them in the neutron and they cancel to 0. The whole pattern of charge in the nucleus falls out of these 2 simple quarks and how many of each you stack. But the quarks are never alone, and they are never still. They are bound together by a force unlike any in everyday life, carried by particles called gluons, named because they glue the quarks together. The gluons stream between the quarks in enormous numbers, and the quarks and gluons together churn inside the proton in a roiling, restless storm. The clean picture of 3 tidy balls is only the barest sketch. The real proton is a seething interior, dense with motion and force. This force has a strange and important habit. The electromagnetic force and gravity both weaken with distance, fading as things move apart. The force between quarks does the opposite. Pull 2 quarks apart and the force between them does not fade. It stays strong, or even grows, like a rubber band that pulls harder the more you stretch it. This is why no one has ever caught a single quark on its own. Try to pull one out, and the energy you pour into stretching the band becomes so great that it snaps into new particles, and you end up with more bound bunches, never a lone quark. Physicists call this confinement. So the proton is not a bag of 3 small heavy grains. It is a knot of light, fast quarks held in a cage of fierce, stretchy force, alive with gluons. The quarks themselves are astonishingly light, and that fact sets up the deepest surprise in this whole story, the one that decides where your weight really comes from. Because if you do the obvious thing, if you take the masses of the 3 quarks inside a proton and add them up, expecting to get the mass of the proton, you do not get anywhere close. The sum falls almost absurdly short. The quarks account for only a tiny sliver of the proton's weight. Nearly all of it is missing, unaccounted for by any of the matter inside. Where the rest of that mass hides is the question of the next chapter, and the answer is the strangest in this entire journey. Let us do the sum that breaks the everyday picture for good. A proton has a mass we can measure precisely. Inside it sit 3 quarks, 2 up and 1 down. Each quark also has a mass set by the Higgs field, which we will come to. So the natural expectation is simple. Add the 3 quark masses, and you should arrive at the mass of the proton. You do not. You arrive at about 1% of it. The up quark and the down quark are extraordinarily light. Together, the 3 quarks in a proton account for only around 1/100th of the proton's total mass. The other 99% is simply not there in the form of quark matter. You have added up all the substance in the proton, all the actual particles of matter, and you have come up with almost nothing. Sit with that, because it overturns everything the kitchen scale taught us. The counting picture said mass is the sum of the masses of the parts. Bring the parts together, add their masses, and you have the whole. For a proton, this fails completely. The parts weigh almost nothing. The whole weighs nearly 2,000 times more than its quarks. The mass did not come from the matter inside. This is not a small discrepancy to be tidied up later. It is the rule, not the exception. Protons and neutrons make up essentially all the mass of every atomic nucleus, and nuclei make up essentially all the mass of every atom, and atoms make up you. So this missing 99% is not some obscure fact about a single particle. It is the origin of almost all the weight in your body, in the chair you sit on, in the planet, in the stars, and it is not made of stuff. Where is it then? The answer points back to the equation from before, the one that said energy has weight. The proton is not mostly matter. it is mostly energy. The fierce force binding the quarks, the storm of gluons streaming between them, the frantic motion of the light quarks trapped in their cage, all of this is energy. And by Einstein's exchange rate, that bound energy carries mass. Almost all the mass of the proton is the weight of the energy locked inside it. Think of the magnets again, squeezed together and weighing very slightly more because of the energy you forced in. Now imagine that effect run to its limit. Imagine a system so full of trapped straining energy that the energy is not a tiny correction to the weight, but nearly the whole of it. That is a proton. Its quarks are like 3 small stones, and the energy of the force holding and whirling them is the vast bulk of what you weigh when you weigh it. This is why the headline about the Higgs is so misleading. The Higgs gives the quarks their small masses, that 1%. It does nothing for the other 99. The overwhelming majority of your weight has a different source entirely, one that was understood before the Higgs was ever found, and one that has nothing to do with a particle bestowing heft on matter. But a claim this strange needs more than a story. It needs proof. Could physicists actually show that the strong force and its trapped energy account for the proton's mass, starting from the bare theory and computing the number? For decades this was beyond reach, the equations too tangled to solve. Then a method called lattice calculation, run on the largest computers available, finally cracked it, and the answer came out right. The proton's mass emerged from energy and force alone, with the quark matter a minor footnote. How that works is the heart of the next chapter. The strong force is the strongest of nature's 4 forces, and the least familiar, because it never reaches beyond the nucleus. It binds quarks into protons and neutrons, and binds those into nuclei, using the gluons as its messengers. Its formal theory, worked out in the early 1970s, is called quantum chromodynamics, from a Greek word for colour, because physicists labelled the strong charge with the names of colours, though it has nothing to do with real colour at all. Here is the feature that makes mass from almost nothing. In the everyday forces you know, the carrier is neutral. Light, the messenger of electromagnetism, carries no electric charge itself, so beams of light pass straight through each other. The gluon is different. The gluon carries the strong charge it transmits. Gluons pull on quarks, and they also pull on one another. The force feeds back on its own messengers, and that feedback is what makes the strong force so fierce and so strange. Because gluons act on gluons, the field between quarks does not spread out and weaken the way an electric field does. It pulls itself into a tight tube, a narrow string of intense force running from one quark to another. Stretch the quarks apart and you stretch the tube, and the energy stored in it climbs steadily, like a rubber band that never reaches its limit. This is the confinement we met before, and the energy in those tubes, together with the energy of the quarks racing inside, is the bound energy that becomes the proton's mass. For years this was a beautiful argument that no one could check with hard numbers, because the equations of the strong force cannot be solved with pen and paper. So physicists turned to a different method. They imagined space and time not as a smooth continuum, but as a fine grid, a lattice of points, and they computed the behaviour of quarks and gluons at every point using immense computer power. The technique is called lattice quantum chromodynamics, and it lets the equations be solved by brute calculation rather than clever algebra. The lattice calculations were enormous, running for months on the fastest machines in the world. And they worked. Starting from the bare theory of quarks and gluons, with the quark masses set very small, the calculations produced the mass of the proton, and the mass of the neutron, and the masses of related particles, all matching the measured values to within a few percent. The number that had seemed like a mystery came straight out of the energy of the strong force. This was the proof that mass can be made with almost no matter at all. The quarks supply about 1%. The rest is the energy of confinement, the energy of the gluon tubes and the trapped, whirling motion inside. It is mass without mass, weight conjured from the binding of nearly massless parts. The phrase that physicists use for it is exactly that, mass without mass, and it captures something true about the world. Most of what is heavy because of energy held in place, not because of an abundance of substance. So the deepest source of your weight is not a particle that hands out mass. It is a force, the strong force, doing what it does inside every proton and neutron in your body, holding light quarks in tight, energetic cages. The mass of those cages, by Einstein's rule, is the mass you carry. This is the answer to the original question, the number on the scale, for the great bulk of that number. It comes from bound energy in the nuclei of your atoms. The Higgs, the particle the headlines crowned, has barely entered the story. Before we turn to what it does do, it is worth pausing to make this personal, to say plainly what it means that almost all of you is energy and motion, not stuff. That is the next short chapter. Stand on the scale one more time and read the number. Now you know most of what it is measuring. It is not, in the main, the amount of matter in you. It is the energy bound inside the nuclei of your atoms, the energy of the strong force holding quarks in their cages, weighed by Einstein's exchange rate between energy and mass. Around 99% of your weight is this trapped energy and the motion that goes with it. Only the last sliver is the mass of the matter itself. Try to feel how far this is from how you experience your body. You feel solid, continuous, made of substance. You bruise, you bleed, you fill a chair. Yet the solidity is mostly empty space and held energy. The atoms are nearly all void. The nuclei, where the weight lives, are tiny knots of force, and the force, not the grains, is what the scale reads. You are, by weight, far more like a standing storm than a pile of bricks. There is a clean way to say it. If the strong force could be switched off, and only the bare matter of your quarks and electrons remained, weighed without any binding energy, you would weigh about 1/100th of what you weigh now. A person of 70 kilograms would drop to well under a single kilogram of actual matter. The other 69 kilograms are energy, held in place by the strong force given weight by the relation between energy and mass. This is the fact the famous headline buried. When the Higgs was found, the world heard that here, at last, was the origin of mass, the source of the heft of all things. But the Higgs has nothing to do with this 99%. It does not touch the strong force. It does not bind the quarks. It plays no part in the energy that makes up nearly all of you. Your weight was explained, in its great bulk, by quantum chromodynamics and the lattice calculations before the Higgs was ever confirmed. So if someone tells you the Higgs gives you your mass, you can answer gently that it gives you about 1% of it. The rest is the strong force and energy and the deep strangeness that the heaviest thing about you is not substance but binding. That is a stranger and a finer truth than the headline, and it is the one the physics actually supports. And yet the Higgs is not a fraud. It solves a real and serious problem, one that has nothing to do with the bulk of your weight and everything to do with the very possibility of matter as we know it. There is a small set of particles, the truly fundamental ones, with no inside and no parts, and for them the question of mass is genuinely deep. For those particles the Higgs is the answer, and without it they would all be massless, and the universe could not hold together as it does. To see why, we have to leave the comfortable world of protons and energy and step into the stranger logic of fundamental particles, where the rules of the theory left to themselves forbid mass entirely. The electron, the quark, the carriers of the weak force, all of them, by the deep symmetry of the equations, should weigh nothing at all. That they weigh anything is the puzzle the Higgs was invented to solve. So we change direction. We have followed your weight down to its source and found it in the strong force. Now we turn to the 1%, and to the particles for which even a 1% mass is a mystery, and we ask the question the Higgs was truly built to answer. Why do the fundamental particles have any mass at all, when the cleanest version of the theory says they should have none? Step away from the proton now, with its borrowed weight of energy, and look at the particles that have no inside at all. The electron is one. As far as anyone can tell, it is a true point, with no parts, nothing smaller within it. The quarks are the same, point-like and partless. So are the particles that carry the forces, the photon of light, and the W and Z particles that carry the weak force. These are the fundamental particles, the ones not built from anything else. For them, mass cannot come from binding energy, because there is nothing inside to bind. So we ask of these particles the question we asked of the proton, and this time the easy answers are gone. Why does an electron weigh anything? It has no parts whose energy could add up. Its mass is not the weight of trapped force. If it has mass, that mass must come from somewhere outside the particle itself, from the space it moves through. And that is exactly what the Higgs provides. This is the real job of the Higgs, and it is much narrower than the headline suggests. The Higgs does not give mass to protons and neutrons in any important way. It gives mass to the fundamental particles, the electron, the quarks, the W and the Z, the ones with no inside. For these, it is the whole story. Without the Higgs, every one of them would be massless, racing at the speed of light, unable to settle into atoms or matter at all. To feel why this is a deep problem and not a simple one, you have to understand something about how modern physics is built. The theory of particles is built on symmetries, on the idea that the laws stay the same under certain changes. These symmetries are not decorations. They are the source of the forces themselves. The requirement that the laws stay unchanged under a particular symmetry forces a force to exist with its own carrier particle. Electromagnetism, the strong force, and the weak force all arise this way, each demanded by its own symmetry. But these same symmetries, the ones that give us the forces, carry a harsh condition. For the symmetry to hold exactly, the carrier particles must be massless. A massive carrier would break the symmetry and wreck the theory, making it spit out nonsense, infinities that cannot be tamed. So the very principle that gives us the forces seems to insist that their carriers weigh nothing. For the photon, this is fine. The photon is massless, and light moves at light speed, and electromagnetism reaches across the universe. For the weak force, it is a disaster. The weak force does not reach across the universe. It acts only across distances far smaller than a proton, dying away almost instantly. A force with such a tiny reach must be carried by heavy particles, because the heavier the carrier, the shorter the reach. So the weak force demands massive carriers, the W and the Z. Yet the symmetry that creates the weak force demands they be massless. The theory wants two contradictory things at once, and as written, it cannot have both. This is the crisis the Higgs was invented to resolve. It is not the comfortable question of why a proton is heavy. It is a sharp contradiction at the foundations. The symmetry that gives the weak force its existence forbids its carriers from having mass, and yet those carriers are plainly heavy, among the heaviest particles known. something has to give. Either the beautiful symmetry is wrong, and with it the whole structure of the theory, or there is a way for the symmetry to be true in the laws, while the world built from those laws looks unsymmetric. That second possibility, that a perfectly symmetric law can produce an unsymmetric world, is the key idea. It is called spontaneous symmetry breaking, and it is where we go next. To see why a symmetry forbids mass, we need to look at what these symmetries actually are. They are called gauge symmetries, and the word gauge comes from an old idea about measuring, about choosing a reference that should not affect the physics. A gauge symmetry says that you can change a certain quantity differently at every point in space, and the laws of physics must not notice. Nothing measurable is allowed to depend on your choice. Take electromagnetism as the gentle example. Every charged particle has a quantum property called its phase, a kind of internal clock hand pointing in some direction. The gauge symmetry of electromagnetism says you may spin that clock hand freely and differently at every point in space and time, and no experiment should be able to tell. For the laws to stay blind to this free spinning, something has to step in and compensate, to carry the adjustment from point to point. That something is the electromagnetic field, and its particle is the photon. The force exists because the symmetry demands a field to keep the laws unchanged. The same logic, applied to other internal properties, gives the other forces. The weak force comes from a symmetry that lets you rotate particles among themselves, turning an electron into its partner, the neutrino, freely at every point. Keeping the laws unchanged under that rotation demands carrier fields, and those are the W and the Z. The strong force comes from a richer symmetry among the colour charges of quarks and demands the gluons. In each case, the carriers are not added by hand. They are summoned into the theory by the insistence that the laws ignore a local change. Now comes the hard condition. For this whole scheme to work, for the carrier to do its compensating job perfectly, the carrier must be massless. The reason is subtle but firm. A mass term for the carrier, written into the equations, is a quantity that does notice the gauge change. It is not blind to the spinning of the clock hand. Insert it, and the symmetry is broken by hand, and the delicate machinery that made the theory sensible falls apart. The infinities that the symmetry had quietly cancelled come roaring back, and the theory loses its power to predict anything at all. So the rule is stark. Gauge symmetry gives you forces, but it gives you massless carriers, with no exception built in. You cannot simply write a mass into the equation for the W particle the way you might write a mass for a baseball. The symmetry refuses it. The moment you do, the theory stops being a theory and becomes a machine that produces only nonsense. For the photon this costs nothing, since the photon really is massless. For the gluon, also massless, the same. But the weak force, as we saw, must be carried by heavy particles, or it could not have its tiny reach. So here the symmetry and the world collide head-on. The symmetry that creates the weak force forbids the very mass that the weak force's behaviour requires. This is not a loose end. It is a flat contradiction, and in the early 1960s it sat at the centre of particle physics like a locked door. Physicists faced a sharp choice. They could abandon gauge symmetry for the weak force and lose the only known way to build a sensible theory of forces. Or they could keep the symmetry and find some way for the carriers to be massless in the deep equations while behaving as heavy particles in the world we measure. The first path led nowhere. The second sounded almost like cheating. A law that is symmetric while its consequences are not. And yet that second path turned out to be exactly how nature works. The clue came not from particle physics at all. but from the humble physics of magnets and supercooled metals. We turn to that clue next, step back from the equations and look at what the weak force actually does in the world, because its heaviness is not a guess. It is forced on us by how the force behaves. The weak force is the one responsible for a certain kind of radioactive decay, where a neutron inside a nucleus turns into a proton, spitting out an electron and a ghostly particle called a neutrino. This is beta decay, and it is the reason some atoms are unstable and part of the chain that lets the sun burn at all. In 1933, Enrico Fermi wrote the first real theory of this process. He treated the decay as happening at a single point, all the particles meeting in one spot with a certain strength. His theory worked beautifully at low energies, and it still carries his name. But it had a flaw that grew worse the harder you pushed it. At high energies, Fermi's theory predicted probabilities greater than 1, which is meaningless, like saying something is more than certain to happen. The theory was a good approximation that had to break down somewhere. The cure was to stop treating the decay as a single point event and to give it a carrier, a particle passing between the neutron's quarks and the outgoing electron, the way the photon passes between charged particles. That carrier is the W, but the weak force has a peculiar signature that the photon does not share. It is incredibly short-ranged. Electromagnetism reaches across a room, across the solar system, across galaxies. The weak force reaches across a distance smaller than 1,000th the width of a proton, and then it is simply gone. The range of a force is set by the mass of its carrier. A massless carrier, like the photon, gives a force of unlimited reach, fading slowly with distance but never stopping. A massive carrier gives a force that dies away sharply, and the heavier the carrier, the shorter the reach. From the tiny reach of the weak force, physicists could estimate how heavy its carriers had to be, long before anyone saw them. The W and Z had to be enormously massive, around 80 to 90 times the mass of a proton, among the heaviest particles in all of nature. So here is the plain collision, stated in terms of facts rather than theory. The photon is massless, and electromagnetism reaches forever. The W and Z must be heavy, because the weak force reaches almost nowhere. These are not philosophical points. They are measured. Beta decay happens, the sun shines, the weak force has a reach you can determine from experiment, and that reach demands heavy carriers. And yet the gauge symmetry that creates the weak force in the first place insists that its carriers be massless, exactly like the photon. The theory, in its clean and beautiful form, predicts 3 more massless carriers alongside the photon. 4 siblings all weighing nothing. Nature has produced 1 massless photon and 3 heavy carriers instead. The symmetry says 4 massless. The world shows 1 massless and 3 heavy. The prediction is simply wrong about 3 of the 4. This is the massless mistake, and it is a serious one. It is not a small numerical disagreement. It is the difference between a particle that weighs nothing and one that weighs as much as a whole atom of a heavy element. The cleanest theory we had got the masses of 3 of the 4 force carriers completely wrong, predicting 0 where nature shows something vast. A mistake this size usually means a missing piece, something the clean theory left out that the real world contains. The question was what? What could be present everywhere, in all of space, that leaves the photon untouched and weighing nothing, while loading the W and Z with the mass of an atom? The first hint of an answer came from a cold and unlikely place. The physics of metals chilled until they lost all electrical resistance. We turn there now. The clue came from superconductors. Metals cooled until they carry electric current with no resistance at all. In the 1950s, physicists studying these cold metals noticed something curious about how they treat magnetic fields. A magnetic field can pass freely through ordinary space, reaching far. But inside a superconductor, a magnetic field cannot get in. It is expelled, and if it is forced in, it dies away over a tiny distance, exactly as if the photon, the carrier of the magnetic field, had suddenly become heavy inside the metal. This was the missing idea in disguise. Inside a superconductor, the massless photon behaves as a massive particle, its reach cut short, because of the medium it is moving through. The metal is filled with a sea of paired electrons that respond to the field and choke it off. The photon has not changed. The space it moves through has changed, and that change gives the force a short range, the very thing a mass does. A Japanese-born physicist named Yoichiro Nambu saw the deep lesson. The laws governing the superconductor are perfectly symmetric, but the state the metal settles into, the cold sea of paired electrons, is not symmetric. It has picked out a particular arrangement, and the physics that plays out on top of that arrangement looks unsymmetric, even though the underlying laws are not. Nambu realized this could happen in the universe at large. The laws of particles could be perfectly symmetric, while the actual state of empty space quietly broke that symmetry, and the carriers moving through it could gain mass, just as the photon does inside the metal. This is spontaneous symmetry breaking, and the word spontaneous is the heart of it. No one breaks the symmetry by hand. The laws keep their full symmetry, but the lowest energy state, the one the world actually rests in, does not share that symmetry, because it has to choose. To picture the choosing, imagine a shape like a sombrero, a Mexican hat, with a raised bump in the center and a circular valley running all the way around the brim. Set a ball at the very top of the central bump. That spot is perfectly symmetric. The ball sees the same valley in every direction, but the top is not where the ball wants to be. It rolls down into the valley, and the moment it lands at one particular point on the circular trough. It had to pick a direction. The law, the shape of the hat, is perfectly round and symmetric. The resting state, the ball sitting at one spot in the valley, has chosen a direction and broken that symmetry. The energy of a field can have exactly this shape. There is a symmetric state, the top of the hat, where the field is zero, and there is a ring of lower energy states around the brim where the field has some value, but the direction of that value is not fixed. The universe, settling into its lowest energy, rolls off the symmetric peak and comes to rest somewhere in the valley, taking on a definite field value everywhere, even in what we call empty space. The law stays symmetric. The world the law produces does not. This was the way out of the crisis. The gauge symmetry of the weak force could remain perfectly intact in the equations, preserving the beautiful machinery that made the theory sensible. But the state of empty space could roll off the peak into the valley, taking on a field value throughout all of space. The carriers moving through that filled space could then behave as massive particles, exactly as the photon does inside a superconductor, while the underlying law stayed untouched. It was an elegant escape, and it almost worked perfectly, but it came with an unwanted guest, a particle that the breaking should produce, but that nobody could find. Dealing with that ghost was the last obstacle, and it is the subject of the next chapter. Spontaneous symmetry breaking solved one problem and seemed to create another. Go back to the ball in the valley of the sombrero hat. Once it has settled at one point in the circular trough, ask what it would take to move it. There are two very different directions it could go. It could try to climb back up the central bump, moving inward against the slope. That takes energy, and the steeper the bump, the more energy it takes. a motion that costs energy to start corresponds, in the language of fields, to a massive particle. So this inward climbing motion gives a heavy particle, and that one turns out to be real and important. We will meet it as the Higgs boson itself. But the ball could also move the other way, around the circular valley, along the flat bottom of the trough. This direction is level. It costs no energy at all to slide along the brim, because every point in the valley is at the same height, and a motion that costs no energy corresponds to a massless particle. So the breaking of the symmetry produces, alongside the heavy particle, a massless one, born from the freedom to slide around the valley for free. This massless particle is called a Goldstone boson, after Geoffrey Goldstone, who showed in the early 1960s that it must appear whenever a continuous symmetry of this kind is spontaneously broken. The result became known as Goldstone's theorem, and it was airtight. Break such a symmetry and you are forced to produce a massless particle, one for each direction the system is free to slide without cost. This was a disaster for the weak force idea. A new massless particle would be a major thing, easy to produce and easy to detect, a particle that interacts and shows up in experiments. Yet no such particle existed. Nobody had ever seen it. The theory had been built to explain why the W and Z are heavy, and in doing so it had conjured a massless particle that nature flatly refused to provide. The cure had a side effect worse than the disease. For a while, this seemed to kill the whole approach. You could have the elegant symmetry breaking, but it dragged in an unwanted massless particle that the world did not contain. Goldstone's theorem looked like an iron law, and it appeared to forbid exactly the solution physicists wanted. The door that had opened a chapter ago seemed to slam shut again. The escape was subtle, and it is one of the most beautiful turns in all of physics. Goldstone's theorem holds for an ordinary symmetry, the kind with no force carrier attached. But the weak force symmetry is a gauge symmetry, and a gauge symmetry comes with its own carrier particles, the would-be massless W and Z. When the symmetry is a gauge symmetry, something different happens. The unwanted massless particle does not survive on its own. Instead, it merges with the force carrier. Picture it almost physically. A massless force carrier, like a massless photon, moves only in certain ways with a limited set of motions available to it. A massive particle has one more way it can move, an extra degree of freedom. The unwanted massless Goldstone particle is exactly that missing piece. When the gauge carrier and the Goldstone particle come together, the carrier absorbs the Goldstone, takes on its extra motion, and in doing so becomes massive. The unwanted particle does not appear in the world as a separate thing. It is swallowed, and its disappearance is precisely what makes the carrier heavy. So the side effect cancels the disease. The massless particle that should have appeared is eaten by the very carrier whose mass it provides. Nothing is wasted, and nothing extra is left over. This swallowing is the true mechanism, and the people who worked it out in a single remarkable year are the ones whose names the particle now carries. That year and those people are next. The solution arrived in a rush, in a single year, from several people working separately who did not know how close the others were. The year was 1964, and it produced 3 papers from 3 groups, all reaching the same mechanism within months of one another. The first to publish were 2 physicists in Brussels, Robert Brout and Francois Englert. Brout was American-born and had moved to Belgium. Englert was Belgian, a survivor of the war who had been hidden as a child because he was Jewish. They worked as the closest of partners for decades. In the summer of 1964, they showed how a gauge field could acquire mass through a field that filled space and broke the symmetry without leaving behind the forbidden massless particle. Almost at the same moment, working entirely alone in Edinburgh, a quiet English physicist named Peter Higgs reached the same result. Higgs was the one who pointed out something the others had not stressed, that the mechanism predicted a new massive particle of its own. The heavy inward motion of the ball climbing the bump in the hat. His first short paper on this point was turned away by a journal as not obviously relevant to physics. He added a sentence naming the new particle's existence, sent it to another journal, and it was accepted. That added particle is the one that now bears his name. A third group, 3 physicists working in London, Gerald Guralnick, Carl Hagen, and Tom Kibble, arrived at the mechanism independently as well, with an especially careful treatment of how the unwanted massless particle is removed. Their paper came just after the others, and for years their contribution was less remembered, though it was every bit as rigorous. All 3 groups had, within a few months, solved the same deep problem in the same essential way. None of them, in truth, was working entirely without precedent. A few years earlier, the American physicist Philip Anderson, studying superconductors, had pointed out that inside such a metal the photon effectively gains mass, and had suggested that the same idea might rescue particle physics from its massless carrier problem. Anderson saw the heart of it in the language of solid materials. What the 1964 papers did was carry the idea fully into the world of fundamental particles, with the mathematics that particle physics required. So the mechanism has many parents, and its fairest name lists several of them. It is often called the Brout-Inglet-Higgs mechanism, honouring the 3 who published first, and sometimes a longer name is used to include all 6 physicists. The single new particle, the heavy one Higgs had emphasised, came to be called simply the Higgs Boson, and the name stuck to the whole idea, fairly or not. When the prize finally came, in 2013, it went to Higgs and Englert. Brout had died 2 years earlier and could not share it, a loss his colleagues felt keenly. What all of them had shown was this: a single field, present throughout all of space, could settle into the valley of the sombrero, taking on a value everywhere, even in the emptiest vacuum. That field would break the weak symmetry spontaneously, in the law's own quiet way. The W and Z carriers, moving through the filled space, would swallow the would-be massless particles and become heavy, while the photon, which does not feel this particular field, would sail on untouched and massless. And there would be one leftover particle, the field's own heavy vibration, waiting to be found someday as proof that the whole picture was real. It was a complete and self-consistent answer to a contradiction that had blocked physics for years, but it rested on a strange claim about the universe, that empty space is not truly empty, that it is filled everywhere with a field that has a value even where there is nothing else at all. That claim, the field that fills space, is the one we examine next. The strangest part of the whole idea is what it says about empty space. We tend to think of the vacuum as nothing, a region with everything taken out. The Higgs picture says that even in the emptiest vacuum, with every particle removed and every other field at rest, one field remains, and it is not zero. It sits at a definite value everywhere, throughout all of space, the way the ball sits in the valley of the hat. This is the Higgs field, and its presence is the deepest claim in the story. To be careful about what a field is, start with one you already know. A magnetic field fills the space around a magnet, stronger near the poles, weaker far away, and it points in a direction at every point. A field is just a quantity that has a value at every point in space. Most fields are zero in empty space, away from any source. Remove the magnet and its field falls to nothing. The Higgs field is different. It does not need a source. Its lowest energy state, the state empty space settles into, is not zero but a fixed value, the same everywhere. The value of the Higgs field in the vacuum is a real, measured number. It is about 246 in the natural units particle physicists use, where it is counted in billions of electron volts. The exact figure matters less than the fact that it is fixed and the same throughout the universe as far as we can tell. Every point of space, the space inside you, the space between the stars, the space in the most perfect vacuum ever made in a laboratory, carries this same steady field value. Unlike a magnetic field, the Higgs field has no direction you could point to in ordinary space. It does not push things along or curve their paths the way a magnetic field bends a moving charge. It is a different kind of field, a scalar field, meaning it has only a value, a strength, with no direction. This is part of why it can fill all of space evenly, without singling out any place or any direction, without giving the universe a built-in arrow. It is uniform, directionless, and always present. That uniformity is essential. If the Higgs field pointed somewhere, space would not look the same in all directions, and we would see the effect in the motions of particles and light. We do not. The field's value is the same and directionless everywhere, which is why we never notice it directly, the way a fish might never notice the water it has always swum in. The Higgs field is the water we have always swum in, the constant background of the vacuum itself. And this is the field whose value gives the fundamental particles their mass. The number on the scale, for the small fundamental part, traces back to this one steady value filling space. The W and Z are heavy because they move through this field and interact with it strongly. The electron has its small mass because it interacts with this field weakly. The photon is massless because it does not interact with this field at all. The whole spread of fundamental masses comes from how strongly each particle feels this single uniform field that fills the vacuum. It is worth pausing on how bold this is as a claim about reality. It says the emptiness around you is not empty. It says there is a presence of a kind in every cubic inch of the universe, quiet and uniform and undetectable in ordinary life, and that this hidden presence is the reason the fundamental particles weigh anything at all. For decades this was a claim on paper, an elegant idea that fit the equations. Whether the field was truly there, with its own particle to prove it, would not be settled until 2012. But before we follow the long hunt for that proof, we need to understand the mechanism itself more closely. How exactly does a particle moving through this field acquire mass? And why is the popular picture of the field as a kind of molasses dragging on particles quietly wrong? That is where the second half of this story begins. The most common picture of how the Higgs gives mass is also the most misleading. You have probably heard it. Space is filled with the Higgs field like a pool filled with syrup or molasses, and particles moving through it are slowed and dragged, and that drag is their mass. It is a vivid image, and it is wrong in a way worth understanding, because seeing why it fails shows you what mass really is. Drag depends on speed. Wade through water slowly and it barely resists, push through fast and it shoves back hard. If the Higgs field were a fluid dragging on particles, a fast particle would feel more resistance than a slow one, and everything moving through space would gradually be brought to rest, slowed by the cosmic syrup until it stopped. Nothing of the kind happens. A particle set moving through empty space keeps moving forever, at a steady speed, undragged. The Higgs field does not slow anything down. Mass is not resistance to motion. It is resistance to a change in motion. A massive particle, once moving, coasts freely. What its mass measures is how hard you must push to speed it up or slow it down, to change how it is going. The syrup picture confuses these two completely. It explains a slowing that does not occur and misses the inertia that is the whole point. Here is the truer picture. The Higgs field has its fixed value everywhere, the steady number sitting in the vacuum. A fundamental particle, like an electron, interacts with that field, and the strength of that interaction is fixed for each kind of particle. Because the field is always there, the particle is always interacting with it, even when sitting still. That constant interaction stores a certain energy in the particle, an energy it carries simply by existing in the filled vacuum. And by the rule that energy is mass, that stored interaction energy is exactly the particle's rest mass. So the mass of an electron is the energy of its quiet, ceaseless conversation with the field that fills all space. The electron is not being dragged, it is being given a rest energy, a weight it carries even at a standstill. By the field it can never leave. Turn the field off, set its value to 0, and the conversation ends, and the electron's mass vanishes, and it would fly at the speed of light like a particle of light. The strength of the interaction is different for each particle, and that is what sets the spread of masses. A particle that interacts strongly with the field carries a large rest energy and is heavy. A particle that interacts weakly carries little and is light. A particle that does not interact at all, like the photon, carries no rest energy from the field and stays massless. The heaviest known fundamental particle, the top quark, interacts most strongly of all, which is why it weighs as much as a whole atom of gold, despite being a single point. This also explains why we never feel the field in daily life. It does not push on you or slow you, because it gives mass through a constant rest energy, not a drag. It acts the same on a particle whether it is still or moving, so it never singles out a direction or a speed. It is silent and uniform, doing its work equally everywhere, which is exactly why it took so long to find. A field that dragged would have been obvious. A field that quietly grants rest energy hides in plain sight. So set the molasses aside. The Higgs field does not gum up the works. It gives each fundamental particle a rest energy, fixed by how strongly that particle talks to the field, and that rest energy is the mass. With this corrected picture, we can return to the original crisis, the heavy weak carriers, and see exactly how they swallowed the unwanted particle and grew heavy while the photon walked away untouched. Recall the crisis the mechanism was built to solve. The gauge symmetry of the weak force demanded 4 massless carriers, 4 siblings all weighing nothing. Nature shows 1 massless carrier, the photon, and 3 heavy ones, the 2 W particles and the Z. The mechanism has to turn 3 of the 4 heavy while leaving the 4th alone, and it has to do this without breaking the symmetry of the underlying laws. Watch how it manages all of that at once. Before the symmetry breaks, the theory has 4 force fields and 1 Higgs field. The Higgs field is not a single quantity here, but has several components, and when it rolls down into the valley of the sombrero and takes on its vacuum value, some of those components become the would-be massless Goldstone particles, the free-sliding motions around the brim. There are 3 of these unwanted massless particles, exactly as many as there are carriers that need to become heavy. Now the swallowing happens. A massless carrier, like a massless photon, has only 2 ways it can vibrate, 2 states of motion. A massive particle has 3, 1 more than a massless one. That extra state is the missing degree of freedom, and it is precisely what a Goldstone particle is, a free motion with nowhere of its own to go. So each of 3 carriers reaches out and absorbs 1 Goldstone particle, taking its motion as the extra state, and in gaining that 3rd way to move, the carrier becomes massive. 3 carriers eat 3 Goldstone particles and grow heavy. The unwanted massless particles vanish as separate things, hidden inside the carriers they made heavy. The numbers balance perfectly. 3 would be massless particles go in. 3 carriers come out heavy, the W in 2 charged versions and the neutral Z. No unwanted particle is left over to embarrass the theory, because each was absorbed. And the symmetry of the deep equations is never touched, because the breaking happened in the vacuum, in the field's choice of value, not in the laws. The contradiction dissolves. But why is the photon spared? Why does 1 carrier stay massless while 3 grow heavy? The answer is that the photon is not simply one of the original 4 fields. The carrier that ends up massless is a particular blend of the original fields, a specific combination that happens not to interact with the Higgs field's vacuum value. That blend has no Goldstone particle to swallow and feels no rest energy from the field, so it stays massless and becomes the photon we know. The other combinations do feel the field, swallow their Goldstone particles, and become the heavy W and Z. The photon is the one direction the broken vacuum leaves alone. This is why electromagnetism reaches across the universe while the weak force dies within a proton's width. They were once a single thing, 4 related fields tied together by one symmetry. The Higgs field, settling into the vacuum, split them. It loaded 3 with mass and left 1 massless, and in that splitting it set the photon free to roam forever while chaining the weak carriers to their tiny range. The picture is now complete in outline. A field fills space, breaks the weak symmetry by choosing a value, hands its Goldstone particles to 3 carriers to make them heavy, spares the photon, and leaves behind 1 extra particle, the heavy inward vibration, as its signature. It is a tight, self-consistent story. But it was, for years, only 1/2 of a larger theory. The half about the weak force. The other half was electromagnetism, and the great achievement of the 1960s was to show that these 2 forces are one. We turn to that unification next. The mechanism for making carriers heavy was a tool, and a tool needs something to build. What it helped build was one of the great unifications in the history of physics. The joining of 2 forces that looked nothing alike into a single thing. The 2 forces were electromagnetism, the familiar force of light and charge and magnets, and the weak force, the obscure short-range force behind certain radioactive decays. On the surface they share almost nothing. One reaches across the universe, the other dies inside a proton. One is carried by the massless photon, the other by the heavy W and Z. And yet they are 2 faces of a single force. The first major step came from Sheldon Glashow, an American physicist, in 1961. He worked out a structure that tied electromagnetism and the weak force together into one framework, with 4 carriers related by a single symmetry. It was mathematically appealing, but it had the fatal flaw we have already met. To make the weak carriers heavy, Glashow had to insert their masses by hand, which broke the symmetry crudely and spoiled the theory. He had the shape of the unification, but not the way to give the carriers mass without wrecking it. The missing piece was the Higgs mechanism, and 2 physicists put it in, independently, a few years later. Steven Weinberg, working in the United States, published a paper in 1967 with the modest title of A Model of Leptons. In it he took the unified structure and let the masses of the weak carriers come from spontaneous symmetry breaking, from the Higgs field settling into the vacuum rather than by hand. The symmetry stayed intact in the laws. The carriers became heavy in the proper way. Abdus Salam, a physicist from Pakistan working in London, reached essentially the same theory at nearly the same time and presented it in lectures. The result is called the electroweak theory, and it says that electromagnetism and the weak force are a single unified force that looks like two only because the Higgs field has broken the symmetry between them. At very high energies, hotter than anything but the earliest universe, the symmetry would be unbroken, the Higgs field would sit at the top of the hat, and all four carriers would be massless and equivalent. The force would show its single nature plainly. Electromagnetism and the weak force would be indistinguishable, two aspects of one thing. But the universe cooled. As it cooled, the Higgs field rolled off the peak into the valley, choosing its value, breaking the symmetry. The single force split into the two we see. The photon stayed massless, and electromagnetism kept its infinite reach. The W and Z grew heavy, and the weak force shrank to its tiny range. The difference between these two forces, so stark in our cold universe, is not fundamental. It is frozen in, a relic of the moment the Higgs field settled, like the single direction a ball picks when it rolls off a round hill. This was a genuine unification, in the deepest sense, reducing two forces to one. It ranked with Maxwell's joining of electricity and magnetism a century before, and with Newton's joining of falling apples and orbiting moons before that. Weinberg, Salam and Glashow shared the Nobel Prize for it in 1979, several years before the heavy carriers were actually seen. That timing matters. The theory was honoured before the W and Z were found, and even before the Higgs boson, because it already worked, predicting the masses and behaviour of the carriers in advance. But for all its beauty, there was a serious worry hanging over it. No one had proven that the theory actually computed sensible answers when pushed hard. It might still collapse into nonsense, into infinities, the moment anyone tried to calculate carefully. Settling that question fell to two physicists in the Netherlands, and it is the next part of the story. A theory in physics has to do more than look elegant. It has to compute. You have to be able to ask it a precise question. How often will these particles scatter? How strongly will this one decay? And turn the crank and get a finite, sensible number you can check against an experiment. For the electroweak theory, in its first years, no one knew whether it could do this. There was a real danger that it could not, that pushing it for precise answers would bury you in infinities, just as the old theories had been buried. The danger comes from how quantum theories calculate. To work out any process, you have to add up not just the simple direct path, but every indirect one, including paths where particles briefly flicker into existence and vanish, borrowing energy for an instant. These fleeting events are called quantum corrections, and there are endlessly many of them of ever greater complexity. When you add them all up, the sums often blow up to infinity, which is meaningless. A theory is only useful if these infinities can be systematically removed, leaving finite answers behind. That careful removal is called renormalization. For the theory of electromagnetism on its own, renormalization had been worked out in the late 1940s, and it succeeded brilliantly, giving predictions matched to experiment to more decimal places than almost anything in science. But electromagnetism has a massless carrier, the photon, and that makes the infinities relatively tame. The electroweak theory had heavy carriers, the W and Z, and heavy carriers were known to make the infinities far more violent and much harder to control. Whether the Higgs mechanism, which gave those carriers their mass, also kept the theory renormalizable was an open and pressing question. If the answer was no, the whole beautiful structure was just a sketch, not real physics. The question was settled in 1971 by a young Dutch graduate student named Gerardus ter Hooft, working under his advisor Martinus Veltman at the University in Utrecht. Veltman had spent years convinced the problem could be cracked, and had built an early computer program to handle the monstrous algebra involved, the endless terms that had to be tracked and combined. Ed Hooft, still in his 20s, found the way through. He proved that the electroweak theory, with the Higgs mechanism giving the carriers their mass, was renormalizable after all. The infinities could be removed systematically. The theory computed. This was the moment the electroweak theory stopped being a promising idea and became a working machine. The proof showed that the carefully arranged way the Higgs field gave mass, swallowing the Goldstone particles, sparing the photon, was exactly what kept the infinities under control. A crude mass inserted by hand would have ruined renormalizability. The Higgs mechanism preserved it. The very feature that solved the mass problem also kept the theory finite, and that was no accident. The two were deeply linked. When Hooft's results spread, the reaction was immediate. Physicists who had ignored the electroweak theory now took it seriously, because it was provably a real, calculating theory. One leading physicist described the change by saying that Hooft's work had made the theory suddenly worth everyone's attention. Predictions could now be made with confidence, including sharp predictions for the masses of the still unseen W and Z particles. At Hooft and Veltman shared the Nobel Prize for this in 1999, nearly 30 years later, long after their work had been thoroughly vindicated. So by the early 1970s, the theory was complete and proven to compute. It unified two forces, gave their carriers mass through a field-filling space, and survived the brutal test of renormalization. Everything rested on predictions that could be checked. The most direct check was to find the heavy carriers themselves, the W and the Z, and measure whether they weighed what the theory said. That hunt, and its success, is where we go next. A theory earns its place by predicting things not yet seen, and then having them found. The electroweak theory made a sharp prediction. The carriers of the weak force, the W and the Z, had to exist, and they had to be heavy, around 80 to 90 times the mass of a proton, with the Z slightly heavier than the W. Nothing that massive had ever been produced. To make such particles, you needed a collision violent enough to concentrate that much energy into a single point by Einstein's exchange of energy for mass. In the late 1970s, no machine on Earth could do it. The answer was built at CERN, the great European physics laboratory straddling the border of Switzerland and France near Geneva. The plan was bold. Take protons and their antimatter twins, antiprotons, accelerate both to enormous energy in a ring, send them around in opposite directions, and smash them head-on. The combined energy of such a collision would be enough to conjure a W or a Z out of the vacuum for the briefest instant before it decayed. The Italian physicist Carlo Rubbia was the driving force behind the idea, pushing hard to convert an existing accelerator into a proton-antiproton collider. There was a serious obstacle. Antiprotons are hard to make and harder to gather into a tight, usable beam. They come out of their production in a wide, unruly spread, far too diffuse to collide efficiently. The solution came from a quiet Dutch engineer and physicist named Simon van der Meer, who invented a technique called stochastic cooling. It worked by sensing the spread of the antiproton beam, computing a correction, and nudging the particles back toward the center over and over millions of times, slowly squeezing the unruly cloud into a sharp, dense beam. Without van der Meer's cooling, there would have been no usable antiprotons and no collisions to study. The machine ran, and two large detectors, called UA1 and UA2, watched the debris of the collisions for the fleeting signature of a W or a Z. The particles themselves vanish almost instantly, far too fast to detect directly. What the detectors see is the spray of lighter particles they decay into, and from that spray, physicists reconstruct what must have been there. It is like identifying an animal you never saw from the tracks it left in fresh snow. In 1983, the signatures appeared, first the W, then the Z, both at the masses the electroweak theory had predicted, both behaving as the theory said they should. The carriers had appeared on schedule, exactly where the theory pointed. This was a triumph of prediction, a case of physicists writing down the mass of a particle years before anyone could make it, and then making it and finding the number right. The masses came out close to the predicted values, 80 times the proton mass for the W and 91 for the Z, confirming that the electroweak unification was not just elegant mathematics, but a true description of nature. Rubbier and van der Meer shared the Nobel Prize the very next year, in 1984, an unusually fast recognition that reflected how decisive the discovery was. With the W and Z found and weighed, almost the entire electroweak theory stood confirmed. The unification was real. The carriers existed and were heavy, just as predicted. The Higgs mechanism that explained their mass had passed every test that could be put to it but one. There remained a single missing piece, the most important and the hardest to find. The mechanism predicted one leftover particle, the heavy inward vibration of the field itself, the Higgs boson. Everything pointed to its existence, but no one had seen it, and finding it would take another 3 decades and the largest machine ever built. That long hunt is the next chapter. Finding the W and Z confirmed that the weak carriers were heavy. It did not prove how they got that way. The Higgs mechanism was the leading explanation, but it rested on the claim that a field fills all of space, and the only way to prove that field is real is to find its particle, the Higgs boson, the field's own vibration. Knock the field hard enough in one spot and it should ring, and that ringing, briefly, is a Higgs boson. Finding one would show the field was truly there. The hunt for it became the longest and most expensive search in the history of physics. The trouble was that the theory did not say how heavy the Higgs boson would be. It predicted the particle's existence and how it would behave, but its mass was a free number the theory left open. So physicists had to search across a wide range of possible masses, not knowing where the particle hid. They needed machines that could reach higher and higher energies, and they needed to rule out, piece by piece, the masses where it was not. The first great hunting ground was a machine at CERN called the Large Electron Positron Collider, or LEP, which ran through the 1990s in a ring 27 kilometers around, buried beneath the countryside near Geneva. It collided electrons with their antimatter twins at high energy and studied the results with exquisite precision. LEP never found the Higgs, but by the time it shut down in the year 2000, it had measured the electroweak theory so finely that it could infer the Higgs must be relatively light, and it had ruled out all masses below about 114 times the proton mass. The particle, if it existed, was above that line. Across the Atlantic at Fermilab near Chicago, a machine called the Tevatron took up the chase. It was a proton-antiproton collider, a descendant of the machine that had found the W and Z, and through the 2000s it pushed into the mass range LEP had left open. The Tevatron narrowed the search further, excluding more of the possible masses and seeing faint early hints, but it never had quite enough energy and enough collisions to settle the question. It was closing in when it was overtaken. The machine that would finish the hunt was built in the same tunnel LEP had used at CERN, the same 27-kilometer ring, refitted with powerful magnets to steer 2 beams of protons around it in opposite directions at nearly the speed of light. It was called the Large Hadron Collider, the largest and most complex machine humanity has ever made. Thousands of physicists from dozens of countries built it, and its detectors over many years at a cost of billions for the central purpose of either finding the Higgs boson or proving it did not exist. There was no middle outcome. Either the field was real and its particle would appear, or the whole picture of how mass arises would need rebuilding. The collider's protons would be smashed together hundreds of millions of times each second, and in a vanishingly small fraction of those collisions, the energy might briefly ring the Higgs field and produce a boson. That boson would vanish almost instantly into a shower of other particles, and two enormous detectors built like cathedrals of sensors around the collision points would record the showers and search them for the particular pattern a Higgs would leave. It was a search for a needle that appeared a few times in trillions of events, buried in a haystack of ordinary collisions. After a slow and careful start, the collider reached the energy and the collision rate it needed, and through 2011 and into 2012 the data piled up. Two independent teams, working separately so they could check each other, combed through it. By the early summer of 2012, both teams were seeing the same thing, a bump in their data at one particular mass, growing steadily more certain. The announcement they were preparing would close a search that had run for nearly half a century, and it came on a date now famous in physics. That day is the next chapter. On the 4th of July, 2012, CERN called a special seminar, and the room near Geneva was packed before dawn. Students had slept in the corridors overnight to get seats. Among the audience sat Peter Higgs, then 83, and Francois Englert, the two surviving authors of the 1964 papers, invited to hear whether the particle their mechanism had predicted nearly 50 years earlier had finally been found. The world watched by video link. Two teams were to present, one after the other. The two teams were the great detector collaborations of the Large Hadron Collider, called ATLAS and CMS, each made of thousands of physicists, each running an enormous detector at a different point on the ring. They had worked in deliberate isolation from each other, analysing their data separately, so that if both saw the same thing it would be a real check and not a shared mistake. One by one their leaders stood and showed their results. Both had found a new particle. Both placed its mass at about 125 billion electron volts, close to 130 times the mass of a proton. The two independent measurements agreed. The signal was strong enough to meet the strict standard physicists demand before claiming a discovery, a level of certainty at which the odds of the bump being a random fluke are smaller than about 1 in a few million. Both teams had crossed that line. A new particle, never seen before, existed at that mass, produced in the collisions and decaying in the patterns expected. The room erupted. Higgs was seen to wipe away tears. When asked later, he said he had never expected to see it confirmed in his lifetime. What the teams had actually detected was not the particle itself, which lives for a span so short it defies imagining, far less than a trillionth of a second, before it falls apart. What they saw was the wreckage. A Higgs boson produced in a collision decays almost at once into other particles, and it can decay in several different ways. In some events it turns into two photons, two flashes of light with a combined energy that betrays the mass of the parent. In others it produces four particles called leptons. The teams counted these telltale events, found more of them than ordinary physics alone would give, and saw the excess pile up at one single mass. That pile up was the particle. It is worth being clear about what was and was not proven that day. A new particle had been found, at the mass where a Higgs boson could live, decaying roughly as a Higgs should. That was a tremendous result, the capstone of a 50-year search and the confirmation, at last, that the field-filling space was real. The headlines, naturally, declared the Higgs boson found and the origin of mass discovered, and in the loose way of headlines this was close enough to true. But careful physicists, even in their celebration, used a more guarded phrase. They said they had found a new particle consistent with the Higgs boson. The word consistent carried weight. Finding a particle at the right mass was not quite the same as proving it was the Higgs in every detail. There are other particles it might conceivably have been, imposters that would show up at a similar mass but behave differently in their finer properties. To be sure this was the genuine Higgs, the field's own vibration, and not some look-alike, the teams had to measure it more closely, testing whether it behaved in every way the theory demanded. So the discovery of 2012 was an arrival, but not the end of the work. It opened a new phase, the careful interrogation of the new particle to confirm its identity beyond doubt. The questions were precise. What is its spin? Does it decay in the right proportions? Does it interact with other particles in proportion to their mass, as a true Higgs must? Answering those questions, and what the answers revealed, is the subject of the next chapter. Finding a new particle at the right mass was a beginning, not a verdict. The teams had to prove the particle was truly the Higgs boson, the vibration of the field that gives mass, and not some other particle of similar weight wearing a disguise. The way to do this was to measure its properties one by one and check each against what the theory demanded of a real Higgs. If even one came out wrong, it was an imposter. If all of them matched, the case was closed. The first property was spin, a kind of intrinsic rotation that every particle carries in a fixed amount. The Higgs boson is unique among known fundamental particles in that its spin should be exactly zero, none at all. Every other fundamental particle has some spin. The force carriers, the photon and the W and Z, carry 1 unit. The matter particles, the electron and the quarks, carry half a unit. The Higgs alone should carry 0, marking it as a different kind of thing, a scalar, the directionless field we met before. By studying the angles at which the new particle's decay products flew apart, the teams confirmed that its spin was indeed 0. The first test passed. The next test was the pattern of its decays. A Higgs boson can fall apart in several ways, into 2 photons, into pairs of heavy particles, into various combinations, and the theory predicts how often each path should occur. Crucially, a true Higgs should decay most readily into the heaviest particles available to it, because it couples to other particles in proportion to their mass. The heavier the particle, the more strongly the Higgs interacts with it, and the more often it decays that way. The teams measured the rates of the different decays and found them falling in line with the prediction, the heavy channels favoured, the light ones rare, in the proportions expected. This proportion to mass was the deepest test of all, because it goes to the heart of what the Higgs is for. The whole point of the Higgs field is that it gives particles mass in proportion to how strongly they interact with it. So the boson, the field's own particle, must also interact with everything in proportion to its mass. A heavy particle should feel the Higgs strongly, a light one weakly. As the teams gathered more data over the years following the discovery, they measured how strongly the new particle coupled to a range of others, from the heavy top quark down to lighter particles, and plotted the strength against the mass. The points fell on the line the theory drew. The coupling rose with mass, exactly as a genuine Higgs requires. One by one the tests came back matching. The spin was 0. The decays fell in the right proportions. The couplings rose with mass along the predicted line. Each measurement could have broken the identification, and none did. With every passing year of data, The new particle looked more and more precisely like the Higgs boson of the theory, the simplest version, behaving just as Weinberg and the others had described it decades before. The guarded phrase, a particle consistent with the Higgs, slowly hardened into a plain statement. This was the Higgs. The achievement was complete and genuine. The field that fills space was real, its particle found and confirmed, the last missing piece of the electroweak theory locked into place. The mechanism that gives the fundamental particles their mass had been verified in nature, not merely written on paper. For the structure built since the 1960s, this was total vindication. And yet, even in that triumph, the limits of what the Higgs explains were already plain to the physicists who built the theory. The Higgs gives the fundamental particles their mass, yes, but it does not say how much. It hands out mass without setting the amounts, and the amounts are wildly different and entirely unexplained. That gap, hidden inside the success, is where the honest trouble begins, and it is the next chapter. Here is the first thing the Higgs does not do, and it sits right at the centre of the theory. The Higgs gives the fundamental particles their mass, but it does not determine how much mass each one gets. The amounts are not predicted by the theory. They are measured in experiments and then put into the equations by hand as inputs, numbers the theory accepts but cannot explain. The Higgs sets up the mechanism by which a particle can have mass. It is silent on why the electron has the particular mass it has, and not some other. Recall how a particle gets its mass in this picture. It interacts with the Higgs field, and the strength of that interaction sets the mass. A strong interaction means a heavy particle, a weak one means a light particle. But the strength of each particle's interaction with the field is its own separate number, fixed by nothing in the theory. There is one such number for the electron, another for each kind of quark, another for each particle that has mass. These interaction strengths are free parameters, dialed in to match what we measure, never derived. And the spread of these masses is staggering, with no pattern anyone can explain. The top quark, the heaviest fundamental particle, weighs about as much as an entire atom of gold. The electron, by comparison, is more than 300,000 times lighter. Between them lie the other particles, scattered across this enormous range with no evident rule. Why should one fundamental point of matter weigh 300,000 times another fundamental point? The theory does not say. It simply takes the numbers as given. It is worth feeling how strange this is. We set out to explain mass, and the Higgs gave us a real and beautiful mechanism for how fundamental particles can have any mass at all, when the symmetry seemed to forbid it. That was a genuine triumph. But it left the actual values, the specific weights of the specific particles, completely open. It is as if we explained how a piano can make sound, the strings, the hammers, the resonance, while having no idea why the keys are tuned to the particular notes they are. The mechanism is understood. The settings are a mystery. These free numbers are not a small embarrassment tucked in a corner. The masses of the fundamental particles are among the most basic facts about our universe, and they have profound consequences. If the electron were much heavier, or the quarks much lighter, atoms and chemistry and stable matter would be different or impossible. The particular values appear to be finely suited to a universe that can hold together and make complex structures, including us. And the theory that supposedly explains mass cannot tell us why they take those values rather than any others. So the honest accounting begins here, in the middle of the success. The Higgs explains how the fundamental particles can be massive. It does not explain their masses. The roughly 1% of your weight that does come from the Higgs, the small masses of the quarks and the electrons in your atoms, has its mechanism explained, but its amounts unexplained. The deepest why these weights and not others, is exactly as open after the Higgs as before it. The discovery did not answer that question, it sharpened it. This is the gentlest of the Higgs's unsolved problems, the free values, because at least the mechanism is sound and the numbers, however unexplained, are stable and consistent. The next problem is sharper and more disturbing. It is not that the theory fails to predict the Higgs's own mass, but that the mass it has seems almost impossible, far lighter than the theory's own logic says it should be, by an amount so vast that physicists call it a crisis. That is the hierarchy problem, and we turn to it now. The Higgs boson has a mass of its own, about 125 times the mass of a proton, the value the collider measured. That number by itself looks unremarkable. The trouble is that the theory's own logic says it should not be anything like that small. When you work through what the theory predicts for the Higgs mass, accounting for everything that should affect it, you get a number vastly larger, and the gap between the natural prediction and the measured value is one of the deepest puzzles in physics. It is called the hierarchy problem. The trouble comes again from quantum corrections, the fleeting flickers of particles popping in and out of existence that every quantity in the theory must account for. For most particles, these corrections are mild. For the Higgs, because it is a scalar with no protecting symmetry, they are not. Every particle the Higgs interacts with contributes a correction to its mass, and these corrections are enormous, pulling the Higgs mass up toward the highest energy scales in nature. The natural size of the Higgs mass, once these corrections are included, is something like the scale where gravity itself becomes strong, a mass perhaps 10 million billion times larger than what we measure. So the theory, left to its own devices, expects the Higgs to be unimaginably heavy. Instead it is light, sitting at a value tiny compared to that natural scale. For this to happen, the giant positive corrections and the giant negative corrections must cancel against each other to an extraordinary precision, leaving only the small remainder we observe. The cancellation has to be exact to something like 30 decimal places. Nudge one contribution in the 30th digit and the Higgs mass, and with it the whole structure of matter would be wildly different. This is what physicists mean by fine-tuning, and it makes them deeply uncomfortable. Imagine balancing a long pencil perfectly on its point and finding it standing there, motionless, for no apparent reason. You would not say it just happened. You would suspect something was holding it, some mechanism you could not see. A cancellation to 30 decimal places feels the same way. It could be sheer coincidence, the numbers happening to line up by luck. But a coincidence that precise cries out for an explanation, for some hidden reason that makes the cancellation natural rather than accidental. To be careful, the fine-tuning is not a contradiction. The theory works. The Higgs mass is what it is, and all the calculations come out matching experiment. Nothing is broken. The discomfort is about naturalness, about whether the value makes sense on its own terms or whether it requires a fantastically improbable accident. Physicists have long trusted that when a quantity looks absurdly fine-tuned, nature usually has a reason, some deeper principle that protects the small value and explains why the cancellation must occur. For the Higgs, no such reason has been found within the established theory. The hierarchy problem is sharper than the puzzle of the free masses, because it suggests something is genuinely missing. The free masses are unexplained numbers, but at least they are stable. The lightness of the Higgs looks like a needle balanced on its point, a value that should not survive without help. So for decades, physicists have expected that help to exist, some new physics beyond the known particles that would step in and stabilize the Higgs mass, removing the need for the absurd cancellation. They had specific candidates in mind, beautiful ideas that would solve the hierarchy problem cleanly. The most popular of those ideas predicted a whole new family of particles that the colliders should have found by now. They have not appeared. The searches have come back empty, year after year, and the silence has become one of the most important results in modern physics, even though it is the absence of a result. What those proposed rescues were, and what their failure to appear means, is the next chapter. If the lightness of the Higgs looks like a needle balanced on its point, the natural thought is that something holds it there. For decades, the favoured candidate for that something had a name, supersymmetry, and it was beautiful enough that many physicists were sure it had to be true. It offered to solve the hierarchy problem cleanly, and it did so by a simple and elegant idea about the giant quantum corrections that threaten to make the Higgs heavy. Recall that those corrections come in two kinds, some pulling the Higgs mass up, some pushing it down, and that they must cancel to 30 decimal places for no apparent reason. Supersymmetry supplies the reason. It proposes that every known particle has a partner, a heavier twin of a different type, and that the corrections from the partners come with the opposite sign to the corrections from the originals. The two sets would then cancel automatically, not by accident, but by the structure of the theory. The needle would be held upright by its own design, and the Higgs would be naturally light without any improbable fine-tuning. It was a stunning idea, and it did more than solve the hierarchy problem. It tidied up other loose ends, hinted at a deeper unity among the forces, and even offered a candidate for the mysterious dark matter that fills the universe. For all these reasons, supersymmetry was, for 30 years, the leading expectation for what lay beyond the known particles. Many physicists built their careers on it. When the Large Hadron Collider was being designed, a major hope was that it would not only find the Higgs, but also discover the supersymmetric partners, the new family of twin particles, completing the picture. The Higgs was found. The partners were not. The collider ran through the 2010s at higher and higher energies, and the teams searched exhaustively for any sign of the predicted twins. They found nothing. No partner particles appeared at the energies where the simplest and most natural versions of supersymmetry said they should be. The searches pushed the possible masses of these partners higher and higher, into ranges where the theory starts to lose the very naturalness that was its main appeal. The elegant solution, if it exists at all, has retreated to a place where it no longer solves the problem cleanly. This long silence is itself a profound result, even though it is the absence of a discovery. It does not prove supersymmetry is wrong, since the partners could still be hiding at energies beyond the collider's reach. But it has badly wounded the simplest and most beautiful versions, the ones that would have made the Higgs mass natural. The clean rescue physicists expected has not come, and other proposed fixes for the hierarchy problem, of which there are several, have fared no better in the search. The collider has explored a vast territory and turned up no new particles beyond the Higgs itself. So the hierarchy problem stands, unrescued. The Higgs is light, absurdly light by the theory's own logic, and the elegant idea meant to explain why has not shown up where it was supposed to. Physicists are left in an uncomfortable place, holding a fine-tuning they cannot justify and watching their favoured explanation fade. Some now wonder whether the universe is simply fine-tuned, perhaps because there are many universes with different values and we live in one of the rare ones suited to us. Others believe a better idea is still waiting to be found. No one knows. This is the second great gap the Higgs leaves open, and it may be the most troubling, because it suggests the known theory, for all its success, is incomplete in a way we do not understand. But there are more gaps still, and the next concerns a particle so light and so strange that the simple Higgs story does not even give it mass in the ordinary way. That particle is the neutrino, and it is the next chapter. There is a particle that pours through you constantly, trillions of them every second, passing through your body and the entire Earth as if neither were there. It is the neutrino, the ghostly particle released in the weak decays we met earlier, when a neutron turns into a proton. Neutrinos barely interact with anything. They have no electric charge, and they feel only the weak force and gravity, so they slip through ordinary matter almost untouched. And for a long time, they were believed to have no mass at all, to be perfectly massless, like the photon. The simple version of the electroweak theory, in fact, predicted exactly that. In the original framework, neutrinos were massless, and the theory had no natural way to give them mass through the Higgs field as written. This seemed fine for decades, because every measurement was consistent with massless neutrinos. They moved at or very near the speed of light, and no experiment showed otherwise. The theory and the observations agreed. Neutrinos weighed nothing. Then, around the turn of the millennium, experiments deep underground revealed that neutrinos do something impossible for a massless particle. They change type as they travel. Neutrinos come in three kinds, and a neutrino born as one kind can, over a journey, transform into another, and then back, oscillating between types as it flies. This oscillation, detected in neutrinos coming from the Sun and from the upper atmosphere, can only happen if neutrinos have mass, because a truly massless particle, moving exactly at light speed, experiences no passage of time in which to change. The discovery of these oscillations proved that neutrinos have mass after all, and it earned a Nobel Prize. The masses are astonishingly small. A neutrino weighs at least 1,000,000 times less than an electron, perhaps far less still, so light that we have not yet measured the actual values, only that they are not zero. And here the simple Higgs story runs into trouble. You could, in principle, give neutrinos mass the ordinary way, by having them interact with the Higgs field like every other particle, but to make them as light as they are, their interaction with the field would have to be fantastically, suspiciously weak, far weaker than for any other particle, with no explanation for why. It would be another unexplained number, and a bizarre one. So physicists suspect neutrinos get their mass differently, through a mechanism the original theory did not contain. The leading idea is called the seesaw. It proposes that there exist very heavy partner neutrinos, far heavier than anything yet seen, and that the lightness of the ordinary neutrinos is tied to the great heaviness of these partners, like the two ends of a seesaw, one end low because the other is high. In this picture, the tiny neutrino mass is not a strangely weak Higgs interaction, but a shadow cast by a very heavy undiscovered particle. It would mean the simple Higgs story is genuinely incomplete for neutrinos, needing new physics to finish it. The seesaw is an idea, not a confirmed fact. The heavy partner neutrinos have not been found, and the true origin of neutrino mass remains open. There is even a deep question about whether the neutrino might be its own antiparticle, which would point to one version of the seesaw over others, and experiments are now hunting for the rare decay that would settle it. For now, the honest statement is that neutrinos have mass, that the plain Higgs mechanism does not naturally supply it, and that the real source is unknown. So the neutrino is a third gap, a kind of matter whose mass the Higgs does not cleanly explain. But there is a far larger gap waiting, one that concerns most of the matter in the entire universe, matter that gets no mass from the Higgs at all, and is not even made of the particles we know. That is dark matter, and it is the next chapter. Everything we have discussed so far, every particle that gets mass from the Higgs or from the strong force, all of it together makes up only a small fraction of the matter in the universe. When astronomers weigh galaxies, by watching how fast they spin and how they bend light, they find far more mass than the visible stars and gas can account for. Galaxies rotate as though gripped by far more gravity than their glowing matter could supply, held together by something heavy that gives off no light at all. This unseen mass is called dark matter, and there is roughly 5 times as much of it as there is ordinary matter. Dark matter is not a minor correction, it dominates. For every kilogram of ordinary matter in the universe, the protons and neutrons and electrons that make up stars and planets and people, there are about 5 kilograms of dark matter, unseen, detectable only by its gravity. It forms vast halos around galaxies and shapes the largest structures in the cosmos. Without it, galaxies would fly apart and the universe would look nothing like it does. Most of the matter holding the universe together is this dark, invisible substance. And here is what it means for our story. Dark matter gets no mass from the Higgs field in any way we understand, because it is almost certainly not made of the ordinary particles the Higgs gives mass to. It does not appear to be protons or neutrons or electrons. It does not shine, does not absorb light, does not take part in the electromagnetic interactions that make ordinary matter visible and solid. It is some other kind of stuff entirely, a particle or particles not in the known roster, and whatever gives it mass is unknown. The Higgs, which the headlines called the origin of mass, has nothing to say about most of the matter in existence. We know dark matter is there with great confidence, because its gravity shows up in many independent ways. It bends the light of distant galaxies, a lensing effect that maps its hidden bulk. It shaped the patterns in the faint afterglow of the early universe, patterns that match a cosmos full of dark matter with remarkable precision. It governs how galaxies spin and cluster. The evidence is overwhelming that something massive and invisible is there. What it is made of, no one knows. Many candidates have been proposed. For years the favourite was a heavy, weakly interacting particle, the kind supersymmetry might have provided, which is one reason the failure to find supersymmetric partners stings doubly. Other ideas point to extremely light particles of a different sort, or to objects and possibilities stranger still. Experiments around the world, buried deep underground to shield them from noise, have been waiting for decades for a single dark matter particle to bump into their detectors. So far, none has been caught. The substance that outweighs everything we can see remains unidentified, so dark matter is the largest gap of all in the story of mass. The Higgs explains the small masses of the fundamental ordinary particles. The strong force explains the bulk of the mass of ordinary matter. But ordinary matter is only a sixth of all the matter there is. The other 5/6 is dark, its mass owed to nothing in our theory, its very nature a mystery. When we say the Higgs gives things their mass, we are speaking about a small slice of the universe. And even this does not exhaust the trouble. Beyond ordinary matter and dark matter lies something stranger still, an energy-filling empty space that makes up most of the universe's total content, and the Higgs field is tangled up with it in the most embarrassing way. The vacuum the Higgs fills should weigh something, and the amount the theory predicts is wrong by the largest margin in the history of science. That is the next chapter. We come to the deepest and most embarrassing trouble of all, and it grows directly out of the central claim of this whole story, that the Higgs field fills empty space with a value everywhere. If empty space is filled with a field sitting at a definite value, then empty space is not empty. It contains energy, the energy of that field holding its value throughout the vacuum. And by the rule that ties energy to mass and to gravity, that vacuum energy should have weight, it should gravitate. it should affect how the universe expands. This is not a vague worry. We can estimate how much energy the Higgs field, sitting in its valley, should pour into every cubic meter of empty space. And there are other contributions too, from the restless flickering of all the quantum fields in the vacuum, the same particles popping in and out that gave us the quantum corrections before. Add up what the theory says the vacuum should weigh, and you get a colossal number, an energy density so vast that it should warp space violently and either tear the universe apart or crush it almost instantly after it began. The universe does neither. It expands gently. We can measure the actual energy of empty space because it shows up as a slight push driving the expansion of the cosmos to accelerate, a phenomenon discovered in the late 1990s and called dark energy. So we have both numbers, the energy the vacuum should have according to the theory, and the energy it actually has according to observation. They do not match. They miss each other by a factor so enormous it is hard to write in words, something like a 1 followed by 120 zeros. The prediction is too large than the measurement by that staggering amount. This mismatch is often called the worst prediction in the history of physics, and the title is deserved. There is no other case where a careful theoretical estimate misses a measured value by anything close to a factor of 10 to the 120. It is not a small error to be patched. It is a complete and total failure of our ability to compute the energy of empty space, and the Higgs field, with its insistence on filling the vacuum with a value, is right in the middle of it. The very feature that lets the Higgs give mass to particles also implies a vacuum energy that is catastrophically wrong. Something must be cancelling that enormous predicted energy, bringing it down by 120 orders of magnitude to the tiny value we observe, but leaving just a faint remainder rather than exactly zero. We have no idea what does the cancelling, or why it stops just short of perfect. It is a fine-tuning far more extreme than the one in the hierarchy problem, the most precise unexplained cancellation in all of nature. The dark energy that the cancellation leaves behind is itself a mystery, a faint push whose origin we cannot explain, governing the long-term fate of the universe. So the Higgs field, the triumph that completed the electroweak theory, also sits at the heart of physics' most spectacular failure. It tells us empty space should weigh an absurd amount. The universe flatly disagrees. Between the prediction and the reality lies the largest gap science has ever produced. Entirely unexplained, we have now walked the full honest accounting from the bulk of your weight that the Higgs never touches, through the masses it explains but cannot quantify, to the deep problems it leaves wide open. It is time to gather all of this into one clear statement, to say plainly what the Higgs solved and what it did not. That summing up is the next chapter. Let us settle the accounts plainly, because the honest picture is both more modest and more interesting than the headline. The Higgs boson was real, it was found, and it solved a real problem. But the problem it solved was narrow and specific, and the great questions about mass remain, most of them open. Holding both of these truths at once is the whole point of this journey. Start with what the Higgs genuinely solved, because it is a true achievement and deserves its honour. The clean theory of forces, built on gauge symmetry, demanded that the carriers of every force be massless. For the photon this was fine, but the carriers of the weak force, the W and the Z, are plainly heavy, and that was a flat contradiction that blocked physics for years. The Higgs mechanism resolved it. A field-filling space breaks the symmetry by settling into a value, the weak carriers swallow the would-be massless particles and grow heavy, the photon is spared, and the underlying symmetry stays intact, keeping the theory able to compute. This let the fundamental particles, the quarks and the electrons and the heavy carriers, have any mass at all without wrecking the theory. That was the crisis, and the Higgs ended it. The discovery in 2012 confirmed the whole structure was correct. Now the limits laid out honestly. First and most important, the Higgs has almost nothing to do with the number on your scale. About 99% of the mass of ordinary matter comes from the energy of the strong force binding quarks inside protons and neutrons, not from the Higgs. Your weight is mostly bound energy, explained by quantum chromodynamics, and it was understood before the Higgs was found. The Higgs gives mass only to the fundamental particles, which make up roughly 1% of you. Second, even for that 1%, the Higgs explains the mechanism but not the amounts. The actual masses of the particles are free numbers, put in by hand, unexplained, spread across a vast range for no known reason. Third, the Higgs's own mass is absurdly light by the theory's own logic, requiring a fine-tuning to 30 decimal places that no one can justify, and the elegant rescue, supersymmetry, has not appeared in the colliders. Fourth, neutrino masses do not come naturally from the simple Higgs story and likely need new physics. Fifth, dark matter, which is 5 times more abundant than ordinary matter, gets no mass from the Higgs and is not even made of known particles. And sixth, the Higgs field implies a vacuum energy that is wrong by a factor of 10 to the 120, the worst prediction in the history of science. So the title of this whole story is fair. The Higgs boson still cannot solve the mass problem, because the mass problem was never one problem. It was a tangle of distinct questions, and the Higgs answered exactly one of them, the narrow question of how fundamental particles can be massive at all without breaking the theory. That answer was beautiful and correct and worth every year of the search. But the bulk of your weight, the values of the masses, the lightness of the Higgs, the neutrinos, the dark matter, and the weight of empty space all lie outside what it explains. This is not a disappointment. It is how science actually looks from the inside, a real answer that sharpens the remaining questions rather than ending them. The Higgs closed one door cleanly and revealed a corridor of others behind it. That is honest progress, the kind that lasts. And it leaves us exactly where we began, standing on a scale with a number under our feet, now understanding far more about where it comes from and how much remains unknown. It is time to return to that scale, and to you, and to say what mass finally means. That is the last chapter. Step back onto the scale where we began and read the number one last time. You know now what it is and what it is not. It is, in its overwhelming bulk, the weight of energy. Almost all of it is the energy of the strong force, locked inside the protons and neutrons of your atoms, holding nearly massless quarks in their fierce cages. Einstein's exchange rate turns that bound energy into the mass you carry. Strip the strong force away and weigh only the bare matter, and you would weigh less than a single kilogram. The rest, the great mass of you, is energy held in place. A thin sliver of the number, about 1%, comes from the Higgs field, the value filling all of space, giving the fundamental particles their small masses through their quiet, ceaseless interaction with it. That sliver is real, and the mechanism behind it is one of the finest achievements of human thought, a contradiction at the foundations of physics resolved by imagining empty space was never empty. But it is a sliver. The headline that crowned the Higgs the origin of mass was reaching for something simpler and grander than the truth. So what is mass, finally, in the plainest words? It is not the amount of stuff you contain. The kitchen scale picture, mass as a count of grains, was a doorway, not the truth behind it. Mass is energy, bound up and sitting still. A proton is heavy because of the energy raging inside it. A fundamental particle is heavy because of the energy of its constant conversation with a field that fills the vacuum. In both cases, the weight you feel is energy that has been trapped, pinned, made to hold its place, so that we perceive the holding itself as solid heft. The most solid fact about you is at bottom a form of restless energy standing still. And the question is not closed. Most of the matter in the universe, the dark matter that outweighs everything visible 5 times over, gets its mass from we know not what. The values of the particle masses are unexplained. The lightness of the Higgs is a needle balanced on its point. The energy of empty space is the worst prediction we have ever made. We understand where your weight comes from, in its great bulk, with real confidence and beautiful proof. We do not understand mass, in full, at all. Both of these are true, and a patient mind can hold them together without strain. There is something steadying in this, if you let it settle. You are made almost entirely of energy, bound into form by forces you cannot see, in a universe most of whose matter we cannot identify and whose empty space hides an energy we cannot explain. You are not a pile of tiny grains. You are a standing pattern of trapped energy, briefly holding its shape, weighing what it weighs because of the deep machinery of the strong force and the quiet field in the vacuum. The number on the scale is a window onto all of it, the known and the unknown together. The next time you stand on that scale in the morning, you can read the number differently. It is not telling you how much stuff you are. It is telling you how much energy the universe has gathered up and held still in the shape of you this morning on this planet for this little while. Almost all of it is the strong force at work in your nuclei. A small part is the Higgs. And a great deal about it, even now, remains an open and honest mystery, waiting in the most ordinary number you will see all day,